If you are a data engineer, you don't need to memorize hundreds of SQL queries. But there are certain SQL patterns that you'll use again and again in real-world projects. In this video, I'm going to show you 10 SQL queries every data engineer should know. We'll cover duplicates, joins, window functions, running totals, missing data, and more. Let's get started. Query 1. Finding duplicate records. This is one of the first things you should check whenever new data lands in your pipeline, because duplicate rows silently corrupt your metrics. Double-counted revenue, inflated user counts, broken joins downstream. Here's how the query works, step by step. Step 1. Group by customer email. Every row that shares the same email address gets collapsed into a single group. If j.smith@mail.com appears 3 times in the table, all 3 rows now belong to one group. Step 2. Count star. For every group we just created, we count how many rows are inside it. A customer with one order has a count of 1. A customer whose email was accidentally inserted 3 times has a count of 3. Step 3. Having count star greater than 1. This is the filter, and notice it's having, not where. Where filters individual rows before grouping. Having filters the groups themselves, after they've been aggregated. We only keep groups where the count is more than 1, meaning we only keep the duplicates. Look at the result table. j.smith@mail.com appears 3 times, a.lee and a.chn appear twice each. Those are exactly the records you'd flag for cleanup before this data moves any further down your pipeline. Query 2. Finding the second highest value. This sounds simple, but it's one of the most common SQL interview questions, and most people get it wrong on the first try. Step 1. Order by salary DESC. Before we can rank anything, we need every salary sorted from highest to lowest. Step 2. Dense_rank. This is a window function that assigns a rank to every row based on that order, 1 for the highest, 2 for the next, 3 for the next, and so on. The key word here is dense. If 2 people are tied for first place, dense_rank gives them both rank 1, and the very next person gets rank 2, no gap. Compare that to plain rank, which would skip straight to 3. That difference matters a lot when you are specifically looking for the second highest value. Step 3. Where RNK equals 2. Once every row has a rank, we simply filter down to the row or rows ranked second. In our example, rank 1 is $100,000, rank 2 is $90,000, that's our answer, and rank 3 is $80,000. Notice this approach works even if there are ties for first place, which is exactly where a naive max-based approach would fail. Query 3. Finding missing records. This is one of the most important checks in any data pipeline, making sure every record that should have arrived actually did. Step 1. Left join warehouse_table. A left join keeps every single row from the source table, no matter what. For each source row, it tries to attach a matching row from the warehouse table. Step 2. When there's no match, you get null. If a source record was never loaded into the warehouse, the join simply can't find a match, so every warehouse column for that row comes back as null. This is the core trick behind this entire pattern. Step 3. Where warehouse ID is null. Now we filter down to exactly those unmatched rows, the ones where the join came up empty. Those are your missing records. In our example, 10,000 records came from the source, only 9,850 made it into the warehouse, which means 150 records are missing, and this query finds every single one of them. This is the exact check you'd run after every pipeline load to catch silent data loss before it reaches a dashboard. Query 4. Getting the latest record per customer. Extremely common when you have a table full of historical events, orders, logins, status changes, and you only want the most current one for each entity. Step 1. Partition by customer_ID. Partitioning splits the entire table into separate mini-groups, one per customer. Think of it as running the rest of the calculation independently, within each customer's own slice of data. Step 2. Order by order_date DESC. Inside each customer's group, we sort their orders from most recent to oldest. Step 3. Where RN equals 1. Row_number assigns 1, 2, 3 and so on within each partition, based on that ordering. Because we sorted newest first, row number 1 is always that customer's latest order. Filtering to RN is equal to 1 keeps exactly 1 row per customer, their most recent record. In our example, one customer has orders on 10th January, 12th, and 15th. 15th January gets row number 1 and is the row we keep, everything else is dropped. Query 5, top n records per group, a natural extension of the previous pattern. Instead of keeping just the single best row per group, we keep the top several. Step 1. Partition by category. Just like before, we split the table into independent groups, this time by product category instead of customer. Step 2. Order by sales DESC. Within each category, products are ranked from highest sales to lowest. Step 3. Where RN less than or equal to 3. Instead of filtering to exactly RN is equal to 1, we widen the filter to keep the top 3 ranked rows in every group. Look at the result. Electronics gives us laptop, monitor, and keyboard as its top 3 by sales. Furniture, completely independently, gives us chair, desk, and cabinet. Change that number in the where clause, and you instantly get the top 5, top 10, or top 1 per category, same pattern, NEN. Query 6. Calculating a running total, the classic pattern behind cumulative revenue charts, running balances, and progress over time metrics. Step 1. Order by order_date. Before we can accumulate anything, we need to define the order rows should be processed in, typically chronological. Step 2. Sum, amount, over, with that same ordering. This is where it gets powerful. Instead of summing the entire table into one number, the window function recalculates the sum for every single row, but only including that row and everything that came before it in the defined order. Step 3. The result grows with each row. Look at the bars. 100 stays 100. Add to 50, and the running total becomes 350. Add 150, it becomes 500. Add 300 more, and it reaches 800. Each new row doesn't replace the total, it builds on top of it. This single window function replaces what used to require a self-join or a slow procedural loop in older SQL approaches. Query 7. Comparing a value with the previous month, the foundation of every month-over-month growth metric you've ever seen on a dashboard. Step 1. Order by month, inside ACTE. We first define the chronological order of our data. Notice we are doing this calculation once, inside A with clause, a common table expression, rather than repeating the same window function multiple times in the final select. That's not just cleaner code, it's also more efficient for the database to execute. Step 2. Lag, revenue. Lag is a window function that reaches backward and pulls in the value from the previous row, in this case, last month's revenue, directly into the current row, side by side with this month's number. Step 3. The growth calculation. Once both values sit in the same row, calculating percent change is simple arithmetic. This month minus last month, divided by last month, times 100. In our example, January was $100,000, February was $120,000. Lag brings January's value into February's row, and the math gives us a clean plus 20% growth figure. Query 8. Finding consecutive events. This is how you detect login streaks, consecutive days of activity, or back-to-back failures in a system. Step 1. Order by event_date. Every event is sorted into strict chronological order first. Step 2. Lag, event_date. Just like the previous pattern, lag pulls the date of the immediately preceding event into the current row, so every row can see when the last event happened. Step 3. DATEDIFF, checking for a gap of exactly 1. We calculate the difference, in days, between the current event and the previous one. If that gap is exactly 1, the two events happened on back-to-back days. String enough of those one-day gaps together, and you've detected a streak. In our example, 10th January, 11th, and 12th, each pair has a one-day gap, which confirms 3 consecutive days of activity. Query 9. Calculating percentage contribution, figuring out what share of a total each category represents. This is behind every % of revenue, or market share, breakdown you've ever seen. Step 1. Group by product. We first calculate the total sales for each individual product. Step 2. Sum of sum, over an empty window. This is the part that trips people up. The inner sum gives us each product's total. The outer sum, wrapped in a window function with an empty over, adds up every one of those already aggregated totals into a single grand total, calculated alongside the grouped rows, in the very same query. Step 3. Divide each product's total by the grand total. That gives us each product's percentage share, multiplied by 100. In our example, laptop makes up 50% of total sales, monitor 30%, keyboard 20%, and together, naturally, they always add up to exactly 100%. Query 10. Our final pattern. Finding missing dates, essential for spotting gaps in daily reports, missed batch jobs, or days with zero recorded activity that a simple group by would never reveal, because there's no row to group in the first place. Step 1. A recursive CTE. This is the key idea. We can't find a missing date using only the data we have, because a missing date, by definition, doesn't appear anywhere in our table. So instead, we generate the full list of dates ourselves. The recursive CTE starts at the earliest event date, then repeatedly adds one day at a time, building a complete, unbroken calendar sequence all the way to the last event date. Step 2. Left join back to the real events table. Just like our missing records pattern earlier, we join this generated date list against the actual events, keeping every generated date, whether or not a matching event exists. Step 3. Where event_date is null. Any generated date that couldn't find a match in the real events table is a date with zero activity, a gap. In our example, 13th January, 14th, 16th, and 17th all have matching events. 15th January does not. That's the missing date this query surfaces automatically. So that's all 10, duplicates, ranking, missing records, latest records, top N, running totals, previous value comparisons, consecutive events, percentage contribution, and missing dates. Notice something. Almost every one of these leaned on a window function, partition by, row_number, lag, or sum over. If you take away one thing from this video, take away this, learn window functions properly, and you unlock the majority of real-world SQL problems you'll ever face as a data engineer. If this helped, like the video, drop a comment with which query you use most often, and subscribe. I'm covering more of these deep dive SQL patterns every week.